So welcome to the 11th session of the problem solving series in this course, Parameterized Algorithms. So I think the recording has started. Yes. So this is the second last week. And after this, we'll have the 12th week. That is one more session. But there's going to be an extra session that we will tell you the date and time. So in today's week, we'll look at some of the questions, assignment questions. These questions were given as assignment questions in the last offering of this course, and I hope that going through these questions will help us solve the assignment questions in this year's offering. So I'll let you read the question. So I hope that you have watched this video, which is module 11, lecture 43. So if you have watched this video, then there is this theorem called two families theorem in this video. And the question is with respect to this theorem. And if you have not watched this video, then I'll encourage you to watch this video and then try to attempt this question. So I'll give you a couple of minutes. So I hope you had a chance to look at the video. So let me give you a rough idea about the theorem. So here is the two families theorem. So there is an universe U, an universe of some elements, and from that universe, uh, two different families of sets are constructed. So one family is the A family, and the other family is the B family. Okay, so in A family, there are M sets. So let us say these sets are denoted as A1, A2, A3 through AM. And in the B family also, there are M sets. Additionally, size of every A family is equal to P, and size of every B family is also equal, that is equal to Q. So for all I in M, this is true. Okay. So these families are constructed from the universe. This is given to you. Additionally, they have the property that AI intersection Bj is empty if and only if I is equal to j. Okay. So it means that AI intersection B, so A1 intersection B1 is empty, but A1 intersection B2 is not empty. Similarly, A1 intersection B3, that is also not empty, and so on. But A1 intersection uh, B1 is empty, A2 intersection B2 is empty, A3 intersection B3 is empty, and so on. So now with this property, so if this property has to be satisfied, then the size of each family, that is M, is at most P plus Q choose Q. Yes. So anyways, so that is not the point. The point is in this question, as far as this question is concerned, this is the property which we are interested in. So which of the following family of sets satisfy the given condition? So this is the condition. So we have to check for each of these options whether this condition is satisfied or not. If this condition is satisfied, then we will say yes, we will pick that option, otherwise not. So let's do it for some of them. So let's do it for the first one. So here in the A family, the 1, 2, 3 sets are there. So therefore in the B family also there are 3 sets. And let us check whether A1 intersection B1, sorry, B1 is here. Yeah, A1 intersection B1 is empty. So as you can see, A1 is 1, 2, 3 and B1 is 4, 5. So there is no intersection. So A1 intersection B1 is empty. Okay. So now let us see whether A1 intersection B2 is non-empty. Yeah, so there is a common element 1. So B2 is 1, 5 and A1 is 1, 2, 3. So 1 is common. So therefore A1 intersection B2 is non-empty. So let us look at A1 intersection B3. Again, 1 is common element. So therefore A1 intersection B3 is non-empty. So with respect to A1, the conditions are satisfied. Now let's verify with respect to A2. So A2 intersection B2 is empty. So 2, 3, 4 and 1, 5 has nothing in common. So therefore this condition is satisfied. Now let's look at A2 and B1. So there's a common element 4. So A2 intersection B1 is 4 and therefore this is not equal to empty. Now let's look at A2 and B3. So B3 is 1, 2 and A2 is 2, 3, 4. So 2 is common. So therefore A2 intersection B3 is non-empty. All right, so far so good. Now we are left to verify whether the condition is satisfied with respect to A3. So let's look at A3 and B3. Is there any common element? No. So A3 intersection B3 is also empty. But we have to check now whether A2 intersection B1 is non-empty. Yes, so sorry, A3 intersection B1. So A3 intersection B1 has two common elements, 4 and 5. So it's non-empty. Again, A3 intersection B2. Again, 5 is common element. So this is non-empty. So the conditions of the two families theorem seems to be satisfied. So I would, if you have any objections, you can let me know, or I will assume that you have understood this. Okay, so this looks like agreeable. So we can agree that this first option, the two families, in fact, satisfy the condition of the theorem. So it does satisfy. So I will say that it satisfies. So I have tick marked it. That means it is satisfied. So now we can verify the other things also, but it takes some time. So let's not verify everything, or let's go to C directly. So how about this two families? So first we'll check. So first we'll check how many sets are there in family A. Three sets. So in family B also there should be three sets. So is this the same as the first one? No, this is different. This is same as the first one. Okay. So let's check A1 intersection B1. A1 intersection B1 itself has 4. So it is non-empty. So it should not be the case, because as per the condition, if I and j are equal, then AI intersection Bj should be empty. So therefore, these families do not satisfy the condition of the two families theorem. So we can right away conclude it without verifying anything else. Is that right? So I hope that it is clear that A1 intersection B1 is non-empty. So therefore, the condition of the two families theorem is not satisfied. Okay. So let's move to the next one. So we are looking at option 4 now. So first thing is to check how many sets are there in family A. There are three sets. So family B should also have three sets. That is correct. So now let's look at A1 intersection B1. It's empty. That is fine. Satisfies the condition. Uh, Now let's look at A1 intersection B2. So this is non-empty. One is common. That is also fine. Satisfies the condition. Now let's look at A1 intersection B3. Again, it is non-empty. 1, 2 both are common. So therefore satisfies the condition of the theorem. Now let's look at A2 intersection B2. It is non-empty. Is it non-empty? There's nothing common, so it is also empty. So 2, 3, 6 and 1, 5, there is nothing common. So A2 intersection B2 is empty. So it satisfies the condition of the theorem. Now let's look at A2 intersection B1. So even E2 intersection B1 is empty. 2, 3, 6 and 4, 5. So nothing common. That is violating the conditions. So A2 intersection B1 should be non-empty, but here in these two families, A2 intersection B1 is empty. So therefore, this condition is not satisfied. Is it clear? So thus, we can right away conclude without verifying anything else that this option also is not satisfying the conditions of the two families theorem. Okay, so let's move to the next one. So we're looking at option 5. So there are three sets in family A and three sets in family B. So this is consistent. So first, let us check A1 intersection B1. So 1, 3, 4 and 2, 5. There's nothing in common, so intersection is empty. That's good. Now let's look at A1 intersection B2. So 1 is common. But in fact, as expected, as per the condition of the theorem, A1 intersection B3. Again, 1 is common. So the condition is satisfied. Now let's look at A2 intersection B2. 2, 3, 4, and 1, 5. Nothing is common. So empty. That is satisfying the condition. Now let's look at A2 and B1. Is there anything common? A2 is 2, 3, 4 and B1 is 2, 5. So 2 is common. So it's non-empty. This is as per the condition. Now let's look at A2 and B3. 2 is common. So the condition is satisfied. Now let's look at A3 and B3. Nothing is common. So that is as per the requirement of the conditions. Now let's look at A3 and B1. 5 is common. This is non-empty as expected. And A3 and B2, that is 5. So again, non-empty as per the condition of the theorem. So this option is in fact satisfying all the conditions of the two families theorem. So we will mark it correct. So I think there is now you have sufficient confidence on how to verify uh, that two families of sets satisfy the conditions of the two families theorem. If you have any doubts, you can let me know. So let us also verify the remaining options for the sake of completeness. So first check how many sets are there in family A. There are 3 sets. So family B should also have 3 sets. That is fine. So let us see what is A1 intersection B1. So 1, 2, 4, and 3, 5. There's nothing in common. So that is all right. Now let's look at A1 and B2. 1 and 4 are common. So non-empty as per the condition. So A1 and B3, again 1 and 2 are common. So non-empty. So following the condition of the theorem. Now let's look at A2 and B2. Is there anything common? No, right? 2, 3, 5 and 1, 4. So intersection is empty. That is as per the condition. Now let's look at A2 and B1. So 3 and 5 are common. So that is as per the condition. Now let's look at A2 and B3. So 2 is common. So that is non-empty intersection. So that is as per the condition. Now let's look at A3 and B3. Nothing common. It's following the condition. Now let's look at A3 and B1. So 3 and 5 are common. So that is non-empty as per the condition. So A3 and B2. Again 4 is common. So that is also a non-empty set. So therefore it's following the conditions of the two families theorem. So we will mark it correct. Is there any doubt? Okay, great. So let's look at the next option. How many sets are there in family A? 3 sets. B also has 3 sets. So this is consistent. So now let's look at A1 and B1. Nothing is in common. 1, 2, 6, and 4, 5. So empty intersection following this condition. So let's look at A1 and B2. So 1 is common between the two sets. So that is non-empty. So following the condition. So let's look at A1 and B3. So it is 1 comma 2, which is again non-empty. So following the condition. So now let's look at A2 and B2. There's nothing in common. So that is empty set. That is as per the condition. So now let's look at A2 and B1 we should take first, no? So A2 and B1. So 4 is common. So non-empty set as expected. Now let's look at A2 and B3. Again, 2 is common, which is non-empty set. So it also follows the conditions of the two families theorem. Now let's look at A3 and B3. Is there anything in common? 3, 4, 5, and 1 comma 2. No. So empty intersection. So A3 and B1, 4 and 5 are common. It follows the condition of the theorem. Now let's look at A3 and B2. That is 5. So non-empty intersection. So everything is as per the conditions of the two families theorem. So therefore, for this option also, we can mark correct. So we are left with the last one. First, check how many sets are there in family A. 3 sets. Family B also should have 3 sets. So this is consistent. Now let's look at A1 intersection B1. So nothing is in common. That is as per the condition. Now let's look at A1 intersection B2. 1 is common. So as per the condition. Now let's look at A1 and B3. 1 is common. So it's following the condition. Even 2 is also common. So A1 intersection B3 is 1 comma 2. So as far as the non-empty set, we are happy. Now let's look at A2 and B2. Oh, A2 and B2 has 6 in common. So that is non-empty. So this violates the condition of the two family theorem. So the condition says that if the indices of A and B are same, then the intersection should be empty. But here the intersection is non-empty. So without verifying anything else, we can conclude that this family A and B, this families A and B do not satisfy the conditions of the two families there. So are there any doubts? So I'll encourage you to ask questions if you have any doubts.
The two families must be of the same size.
Same size, yes.
Okay.
The You mean the number of sets in each family should be
Yes, yes.
yes, 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 that is correct.
Okay.
Okay, so for the sake of completeness, I will also compute this one. Yeah, so let's look at this one again. I think we didn't, yeah, we didn't do this. So A1 intersection B1 is 5. That is as per the condition. So A1 intersection B2 is 1. So that is as per the condition. So A1 intersection B3 is 1 comma 2, again non-empty. So this is good. So A2 intersection B2 is empty, nothing in common. A2 intersection B1 is 3. So that is non-empty. So as per the condition. So A2 intersection B3 is 2. So that is non-empty. So as
Yeah,
per the
this
condition.
satisfies the
All right, all
condition.
right. Okay, okay. So you have also checked the other things. Fine. So we will conclude that this is also fine. Okay, so we can go to the next one.
So it's essentially what this theorem is saying is we have these two families
Yeah,
with
so this is saying that that the size of the family
mm,
cannot exceed
bounded. Okay.
this quantity. So this is a combinatorial result,
Hmm.
and it is in fact encapsulating this condition that with this condition you cannot grow two families of larger size.
This bound is tight as well.
I think yes, I think some families, two families can be constructed that is exactly having this size.
Okay.
Yeah, so I think there is in the book of Bolobash, there's a chapter
Hmm.
on intersecting families. That book on
Existing.
hypergraphs.
Yes.
Yes, yes, yes. So there, this theorem is also there.
Sperner's formula or something.
Is it Sparners? Let me check. Sparner system size. Sparner system is with respect to one family of subsets from the universe.
Hmm. Yeah.
This says that for a finite set S with n elements,
Hmm.
the largest size of a Sparner system, that is a family of subsets where no subset is contained in another,
In the other, yes.
is given by this formula n by 2 factorial.
Yes. I think, but that result, I guess, implies this two families theorem. Something
Okay.
similar, I think I have seen.
Okay, okay. Yeah, this could be possible. But I looked at the proof of this thing. So this
Hmm.
can be also proved from the scratch without depending on this Sparner theorem.
Okay.
Yeah, so we can talk about it offline as well. So let's look at the next question. Oops. Yeah, so this is also on the same two families theorem. So I have, yeah, the two families theorem is here. So we can look at it together. So the question is asking whether the following statement is true or false. So is it possible to have, so you have to, so there's only one family A. So is it possible to have a family A of some size M, where each AI is a set over a universe U? So inverse if is given, let us say, such that every set in the family A is of size P. So it is as per the definition of the two families theorem, as per the statement of the two families theorem. Okay. And the family A satisfies the condition for the two families theorem with itself. Okay. Uh, so what does that mean? So taking Bi is equal to Aj for some J. Yeah. So I think it means the following, that you have only one family. So the family has M sets. So now, of course, if you replicate the same family and call it the other family, then this condition that A1 intersection A1 should be empty, that is not going to happen. But can you find some permutation of the families? So can you say that, okay, I am going to use the same sets from the family, but I'm going to permute it. Okay. Uh, so that now after permutation, so now this one is what I'm going to call B1. This one is what I'm going to call B2 and so on. So now this is the same family but in another order. Then now whether these two families satisfy the two families theorems. So basically whether such a thing can be accomplished. So is the question clear? So I'll repeat the question. So, so if this statement is true, so in case this statement is true, then it should be possible to find M sets A1 through AM from some universe such that every AI has equal size. There is a P. And then for B1, you take some AJ from the family A. For B2, you take some AJ from the family A and so on. So you will obtain M sets, but these M sets are nothing but from the family A itself, but just it's a permutation. Then this family, two family theorem condition should be satisfied. And if this statement is false, then it is not possible to obtain such a permutation at all. So let us take a concrete example. So let us take a concrete example. So I'm going to take some of the sets. So let us say A1, or just I will just take the sets. So A1 is, let us say, 1 comma 2. A2 is, let us say, 1 comma 3. A3 is 1 comma 4. A4 is 2 comma 3. A5 is 2 comma 4. And A6 is 3 comma 4. All right. So what is the universe? It's the union of these things. So it's 1, 2, 3, 4. Then what is P? There is the size of each set. So there are two elements in each set. So P is 2. So now what I want to do is I want to pick one of these sets from here and call it B1, such that A1 intersection B1 is empty set. So of course I cannot take a set that contains 1 comma 2. So of course I have to take 3 comma 4. Is that fine? So if I take 3 comma 4 here as B1, then A1 intersection B1 will become empty. So for 1 comma 3, what do we have to take to ensure that B2 and A2 and B2 intersection is empty? There's nothing in common. So the other two elements have to be taken. So 1 3 is already there. So how about 2 4? Okay. So on, I will write down everything. So 1 comma 4. So the complement of 1 comma 4 with respect to the universe 1 2 3 4 is 2 3. The complement of 2 comma 3 with respect to the universe is 1 4. So the complement of 2 comma 4 with respect to the universe is 1 comma 3. And the complement of 3 comma 4 with respect to the universe is 1 comma 2. Now we are sure that AI intersection BI is empty in all these cases. So all we have to check is AI intersection BJ is non-empty whenever I is not equal to J. That's all we have to check. So let's check these two first. So 2 is in common. Again, 2 is in common. 1 is in common. 1 is in common. 1, 2, both are common. So, I mean, can we just conclude by some observation that A1 intersection BJ is definitely going to be non-empty whenever I is not equal to J? Can we make some observation and make this claim?
Siddharth,
Yes.
so how did you construct this example? To say we have P equal to 2, that means each set has size equal to 2. Now we want
Mhm.
to construct a family which uh, satisfies the condition for the two families here.
That is right. Yes.
So,
So, what is the general trick? That's what you were asking.
hmm,
Okay, okay, okay. So, first, let us verify whether this is correct or not,
okay.
whether this is all right. So, in the universe, there are four elements, and every set has two elements.
So
So,
this P is not, we can take any P.
yes, 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 that
Okay.
we can take. So, I think the small p is taken so that we can verify things
Hmm.
quickly. So, therefore, choose two. There is six possible two element sets. So, all these two element sets I have taken. So now, because I have taken two element sets and the universe is of size 4, so the complement of each two element set can be placed as the corresponding BIs for every AI. So we can ensure this property whenever I is equal to J. But we also have to ensure that for I is
I
not
not
equal to J.
equal to J, they intersect.
So the thing is, So the
This
so
is true.
whenever yes, yes. So whenever I is not equal to j,
Hmm.
ai is not equal to bj. Now I want to say that ai's intersection bj complement, because see, sorry, I'll write down. I'll write down. So I want to check ai intersection bj, but I know that bj is nothing but ai aj's
AJ
complement.
complement.
Okay, so now, so how does it look? So maybe it can happen that ai and aj are disjoint. So in that case, ai intersection aj complement will be ai. But it can happen that ai and aj has some overlap. So even then, aj's complement will have some element with ai. But as long as ai and aj are not identical, there will be some element which is common to ai and aj complement. But then we know that every ai is different from aj. So no ai is identical to another aj. So therefore, this is definitely non-empty. So for so can we do it for p equals to 1? So for in an universe 1 comma 2, so let us say the smallest. So we could do it with 1 comma 2 also, I think. So now we want to check how we'll do it for what is the general trick. So let us say I make families of size 1. So then again it will be satisfied.
Yes, yes. I think basically you take all possible P subsets and the corresponding complement of each set in the
Yes,
not
yes, yes.
not all possible P. P is basically the universe size divided by 2.
Mhm. So therefore the universe size should be even for this
Hmm.
formula to work. So M, that is the total number of sets in each family, should be the universe size. Choose universe size by 2. So in this case, universe size is 4, so 4 choose 2. There were 6 sets in this family. So if the universe size is mod u, then mod u choose mod u by 2 should be the number of sets in each family. Yes, so shall we move on? So let us move on. Yeah, so this question is independent of the videos. Okay, so we want to determine which of the statements are true and which of the statements are false. So let's look at the first question first. Okay, so length of a path is not the number of edges in the path, but the number of vertices in the path. So for example, if I have this path, then I will say that the length of this path is 4 because there are 4 vertices in this path. So similarly, if I have a cycle like this, then I'll say the length of this cycle is also 4, because by convention we are saying that the length of a path or cycle is nothing but the number of vertices in the path of the cycle. So now the question is, if a directed graph G has a directed cycle of length at least k, then it has a path of length at least k. So we want to determine whether this is correct or not. So for example, here is a cycle of length 4. So 1, 2, 3, 4 back to 1. This is a cycle of length 4. But we are dealing with directed graphs. So let us say that there are directions. So this is a directed cycle. It originates at 1 and terminates at 1. But since it's a direction issue. Okay. So now we have a directed cycle of length 4. So it's clear that if we remove the last, or if we disregard the last directed edge, that is the directed edge which is incoming to the source, let us say 1, then we will definitely have a path that uses 4 vertices. So from the cycle, from the directed cycle, if you disregard exactly one of the directed edges, then you will end up with a path. And this directed path is also going to use exactly the equal number of vertices. So the length of the path will be nothing but the length of the cycle. So in general, if there are k vertices forming a directed cycle, so you remove exactly one of the edges and you end up with a directed path of exactly the same length. So therefore, this statement is true. Is that all right? So then let's look at the next statement. It is the complement of this statement. The same thing. If a directed graph G has a directed cycle of length at least k, then it may not have a path of length at least k. That is incorrect, because we have seen that there definitely exists a path of length k because of this argument. So this is incorrect. Uh, yeah, let's look at the next one. So if directed graph G has a directed path of length at least k, so now we are talking about a path. Then it has a directed path of length exactly k. So there is a directed path, and I know that the length of this path is at least k. So it could be even larger than k. So the number of vertices taking part in this directed path is k or more. Then it has a directed path of length exactly k as well. Okay. So if the directed path is of length k, exactly k, then there is nothing to prove. But if the directed path is strictly more than k in length, then we can adjust, or we can obtain a smaller path of size exactly k by removing the extra vertices from the path, or rather disregarding the extra vertices from the path. For example, in this figure, how many vertices are there in this directed path? So 1, 2, 3, 4, 5, 6, 7. So if the value of k is 4, then also this is correct that there is a directed path of length at least 4. Then if we remove the last 3 vertices, or if we disregard the last 3 vertices, then we will end up with a directed path of length 7 minus 4, or rather 7 minus 3, that is 4. So it is always possible to obtain a smaller directed path from larger directed path. So therefore this statement is true, that we can also find a directed path of exactly length k from a larger, potentially larger directed path. Okay. Is there any doubt on this? Okay, so we'll move to the next one. So if a directed graph G has a directed cycle of length at least 2k, okay, then for any edge u comma uv, after contracting the edge uv, the graph still has a cycle of length at least k. So first let us draw this directed cycle. So there is this directed cycle. The direction is, let us say, like this. And the number of vertices participating in this directed cycle is at least 2k. All right. So now you pick any edge in the graph. So let us pick any edge in the graph uv, and you contract that. So what is the contraction operation? That suppose this is your edge, and once this edge is contracted, so all the incoming, so this becomes a super vertex, and all the incoming edges to u and v become incoming edges to the super vertex, and all the outgoing edges from u and v except this edge become outgoing vertices. All right. So after the contraction operation also, the graph still has a cycle of length at least k. Okay, so that we have to prove or disprove. So it is clear that if u and v are both outside the cycle, that means they do not take part in the cycle, then its contraction does not have an effect on the length of this cycle. So we will still have cycle of length at least 2k. But if one of u or v is in the cycle, then we may have to do certain things. So for example, if u was, let us take this. So for example, let's u as u were here and v was here, and there's a uv h, then once it gets contracted, uh, uh, then this supernode uv becomes part of this cycle after contraction. Then again, we'll have this same sized cycle. So there's nothing to worry. On the other hand, if the situation is more complicated, I'll draw here only. So let's say u was outside and v was here. So there's a u to v h. Now after the contraction, the supernode is again becoming a part of the cycle. So we'll again have the same length cycle. So again, we'll have at least 2k length cycle. But if u and v are both part of the cycle, and we have a situation like this, then this is becoming a supernode after the contraction. So there is a cycle. So this is becoming a supernode. So this is one cycle, and this is another cycle. So what is the length of the larger of these two cycles? So this supernode is common to both the cycles. So that means the sum of the nodes participating in the two cycles is, so earlier we had at least 2k. So now two vertices u and v are no more there, but uv, the supernode is appearing in both the cycles. So the question I'm asking is the sum of the lengths of the two cycles which are formed because of the contraction operation, that is going to be what? So two nodes are deleted and the supernode is appearing twice. That is going to be at least 2k. So that means one of the, by pigeonhole principle, at least one of the two cycles, directed cycles, has length k. So that is exactly what I want, because there are two cycles. Overall, the sum of the lengths is at least 2k. So one of the cycles will have length at least k, and therefore this is true. Is that all right? All right. So let's move to the last one. So if a directed graph G has a directed cycle of length at least k, then it has a directed cycle of length exactly k. Okay. So is this true or false? So consider a directed cycle of length at least k. So for example, here is a directed cycle of length 4. Okay. So I can also consider this directed cycle as a directed cycle of length at least 3. That is also fine. So I can consider this to be a directed cycle of length at least 3. Now, if that is the case, their claim is then it has a derivative cycle of length exactly 3 also. But in this figure, we can see there is no derivative cycle of length 3. There's only one derivative cycle of length 4. So therefore, this statement is not true because of this counterexample. All right. So is this all right? Is there any objection to this? No objections? So here, instead of, although it's a 4-length cycle, I'm setting k to 3. So I'm saying that, okay, this can be considered as a derivative cycle of length at least 3. But then here there is no derivative cycle of length exactly 3. So therefore, this statement that there must exist a derivative cycle of length exactly k, that is not true. So therefore, this is false. Is that all right? Okay. So at this point, we can take a small break, 10 minutes break, and we can come again after 10 minutes. But I will show you the next question. Okay, so this question is about matroids. Not get bigger. Okay. So coming back again, it's 7. Let's say we'll come back again at 7:25. So we have 10 to 12 minutes break. We are coming back at 7:25. So welcome back again. So I hope that you had a chance to look at the question. So the question is about matroids. And which of the following families of sets forms a matroid where the universe is the set of vertices of any graph? Okay. So we'll look at all these statements and we'll decide whether we'll, these families are matroids or not, forming a matroid or not. Okay. So here's the first option. The family of sets of vertices inducing a cycle in G. That is, for each cycle C, consider the set VC. Okay. So is it a matroid? So what are the properties of a matroid? We have to first understand that. So one of the properties of the matroid is called the hereditary property. So the hereditary property says that uh, so if A is an independent set of the matroid has a set of so 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 with respect to A, certain sets are independent, and if A is one of these independent sets and B is a subset of A, then B should also be an independent set. Okay. So now in this case, so consider a cycle in the graph. So let us say this is a cycle. Let us say that the vertices of the cycle are 1, 2, 3, 4, 5, and 6. Then any subset of this 6 vertices should also form a cycle. That is the meaning for it to be a matroid. So this is a cycle. So for it to be a matroid, any subset of this, so let's call it A. So any subset, every subset of A should also be a cycle. But is that true? It's not necessary, right? For example, if I remove 1 and this edge is not there, this edge is not there between 2 and 6, then 2, 3, 4, 5, and 6 doesn't form a cycle. So therefore, the hereditary property is not holding. So therefore, this family of sets of vertices inducing a cycle in G is not a matroid. Okay. So is this clear? All right. So let's go to the next one. The family of sets of vertices inducing a forest in G, that is for each forest F, which is an induced subgraph of G, consider the set of vertices in the forest. So the first step is to check whether the hereditary property holds true or not, right? So we're looking at all sets of vertices that induce a forest. So So consider a induced forest. What is the subset of an induced forest? So the question is the subset or is any subset of an induced forest also an induced forest? So if you look at the subset of an induced forest, then can it have a cycle? So in the forest, there was no cycle. So in a subset of it, how can there be a cycle? So it is true that any subset of an induced forest is also an induced forest. So the hereditary property is fine. So that's all right. So the other property that we have to check is called the exchange property. So what is the exchange property? So it's also called the augmentation property. Okay. So it says that if A and B are two independent sets in a matroid such that A is larger than B. So A and B are two independent sets in a matroid and there are more elements in A than in B. Okay. Then there exists an element in A which can augment B. Okay. There exists an element X, let us say, in A which is not there in B, such that if you add X to B, that also forms an independent set. Okay, so the size of B can be augmented. So this can ensure a larger independent set extended by elements of smaller independent sets. Yeah. So now is this exchange property true in this family? Okay. So I'll give you few minutes to think about it. Okay, so I'll give an example. So consider a graph on 5 vertices. So here is a graph. Let me use a different color. A, B, C, D, E are 5 vertices, and the edges are AB, AC, AD, AE, BC, BD, and BE. So let's find mm, so what is it? A forest. Okay, let's find an induced forest. So let us take S to be A comma B. So the induced graph of A comma B is only this edge AB. So this is a forest, no cycles. And let's consider the set P equals CDE, and the induced graph on CDE is uh, so there are no, okay, so it's an empty graph, so there are no edges, right? In the induced graph on CDE, I don't see any edges. But does there exist a vertex in T whose union with S forms a forest? So this is a larger independent set. So in the terminology of Matroids, this is an independent set, this is also an independent set. But can I take an element from T and take union of that element with S so that it also remains an independent set? In our case, independent set means a induced forest. So C if you take, then there is a cycle with AB. If you take D, there is also a cycle with AB. If you take E, there is also a cycle with AB. So therefore, there is no vertex that you can take from T. That union with S will give you a forest. So therefore, the exchange property is not holding true. So the exchange property fails. So therefore, we will say that this family is not a matroid. Right? Okay. Is there any doubts on this? So if this is clear, then we can move to the next question. So I will go to the next page. So I'll copy this. To copy this. Okay, fine. I'll re-import this. So I'm looking at the third family now. So the family of sets of vertices inducing a tree in G. So for each tree T, which is an induced subgraph of G, consider the set Vt. So is this going to form a matroid? So now we consider a induced tree in the graph. So this is an induced tree. All right. So now any subset of this induced, any subset of the vertices forming this induced tree should also form an induced tree. That means connectedness should also be there. That is the hereditary property of the matroid. So is the hereditary property going to be true in this case? So is the meaning of hereditary property in this context clear? So you have a induced tree. Now it takes some subsets. Let us say I don't take this vertex, I take the remaining vertices. So if you look at the induced graph on the remaining vertices, there are multiple trees. So this is one tree, this is one tree, this is one tree, this is one tree. So connectedness is lost. It becomes a forest. So any subset should also be a tree. That is a hereditary property. That's what it says. That if A is in I and B is a subset of A, then B should also be in I. So I is the, in this case, the treeness property. So any subset should also be tree, should also be a tree. This is violated. It's not true. Need not be true. So therefore, since the hereditary property is not true, so even this one is not a matroid. Is that all right? Yeah, I think it's quite late in the evening. You are also tired. So we'll not take, let's say, more than 15 minutes today. So let's also verify the remaining things. So let's go to the next one quickly. Now we're looking at this. The family of independent sets in G. That is, the sets I subset of B such that no two vertices in I are adjacent. So an independent set is a set of vertices such that no two vertices in this set are adjacent. Okay. So now is the family of independent sets in G a matroid? So consider an independent set. Any subset of an independent set is it also an independent set? So that is true, right? So if you have a graph where you have been given a set of vertices which forms an independent set, so any vertex subset of the independent set is also going to be an independent set. So the hereditary property is fine. So we have to only check whether the exchange property holds true or not. So what is the exchange property? Remember, so it is nothing but the ability to augment. That means if there are two independent sets A and B, such that A has more vertices than in B, then there exists a vertex exclusive to A, that means exists in A but not in B, whose inclusion into B is also an independent set. Can we show this? Or is it possible that the exchange property may not be satisfied always? So let me take an example. So let me take a small graph. Here's a small graph. It's a path graph on 3 vertices. So in this graph, B is an independent set and A comma C is also an independent set. So can I take a vertex from A comma C and merge with B so that the resulting set is also an independent set? So if I take A and take union with B, so A and B has an edge, so it's not an independent set. So if I take C and take union with B, B and C also has an edge, so it's not an independent set. So B cannot be augmented by taking a vertex from A comma C. So therefore the exchange property is no more true. So therefore we can conclude that this family is also not a matroid. So far we haven't seen any matroids. Since we have checked already. So the matroid is still evading us. Now let's look at the next one. Now we have vertex covers of G. There is all sets in the subsets of the vertexes such that every edge of G has at least one endpoint in S. So what is a vertex cover? A vertex cover is a subset of the vertices such that every edge of G has at least one endpoint in S. Okay. So now is the set of all vertex covers a matroid. So first, what do you have to verify? Which property shall we verify first? We'll verify the hereditary property first, so that whether a subset of a vertex cover is also a vertex cover. That need not be true. So consider this. Uh, consider this graph. So A and C is a vertex cover, isn't it? So in this graph, A comma C is a vertex cover. Why? Because this edge is covered by A and this edge is covered by C. So you might say that B is also a vertex cover. That is also true. But I'm taking A comma C, which is also a vertex cover. But if the hereditary property has to be true, then any subset of A comma C should also be a vertex cover. But A alone cannot cover this edge and C alone cannot cover this edge. So therefore, neither subset A nor subset C is a vertex cover. Not vertex cover. So therefore, the hereditary property itself is not true. So we don't have to check anything else. We can right away conclude that this family is not a matroid. Is that all right? Is there any doubts on why this is not a matroid? Oh, all right, fine. Since there are no doubts, we can move to the next next family of sets. So the family of sets of vertices S such that GS forms a clique. So what is GS? GS is the subgraph induced by the subset of vertices S. Now is this a clique? So I'll give you a minute to think about it, that whether this is a clique. I mean, matroid. Is this a matroid? So is the subset of a clique also a clique? I mean, so consider a clique and take a subset of the vertices forming the clique. Is the graph induced by this subset also a clique? That seems to be true. So if you have a clique, then you take any subset of the vertices of the clique. These vertices also will induce a clique. So that is by the property of the clique itself. So therefore, the hereditary property is true. Hereditary property is true. There is no doubt about it. But how about the exchange property? Is this true? So remember, what is the exchange property? That if you have two cliques, a larger one and the smaller one, then the smaller one can be augmented by taking a vertex from the larger one which is not in the smaller one. Okay, I'll let you look at the exchange property once again. So this is the exchange property, also called the augmentation property. So now let me take an example. Okay. So now let's take two cliques. So S A comma B is a clique of size 2 and P C D E is also a clique of size 3. It's a triangle. Now can I take some vertex from T? So of course S and T in this case are disjoint. So can I take some vertex from P and take union with A comma B, and that forms a clique as well? So what if I take C? So this is A, B, C a path only. What if I take D? So A, B and D is isolated in the induced subgraph, doesn't work. If I take E, then AB and E is isolated in an induced graph on AB and E. Again, that is not a clique. So in no way we can ensure that A comma B is augmented. So the exchange property fails. So again, we have failed to find a matroid. So again, so we are going to conclude that this is not a matroid. This is not a matroid. Not a matroid. Okay. So we can go to the next one. So now we are going to look at the family of all subsets of VG of size less than or equal to k for a given fixed k greater than or equal to 0. Okay. The family of all subsets of the vertex set of size less than or equal to k for a given fixed k greater than 0. Okay. The first point is, the first thing to verify is whether the hereditary property is true or not. So what is the hereditary property? So in this case, we just want to check whether given a set A and B, which is a subset of A, is B also an independent set. So in this case, what is independent set? That is the size of the subset should be less than or equal to K. So because A has size less than or equal to k, any subset of A should also have size less than or equal to k. So that is immediate. So therefore, the hereditary property is holding true. So it is true, holds. So the hereditary property is actually holding. So we all we need to do now is to check whether the exchange property is holding or not. So how about the exchange property? Okay. So consider two subsets, A and B, or rather S and T. So mod S, the number of elements in S is at most k, and mod T is also at most k. But let us say that mod S is strictly less than mod T. Okay, so that means there exists some x which belongs to T but does not belong to S. Okay, so therefore, if you take union of x with S, all right, so how many elements will be there? So you know that x is one element plus mod S. So what is mod S? So since mod S is less than mod T, so therefore mod S is also strictly less than k. So the number of elements in T is at most k, number of elements in T is at most k, and S has at least one less element than k. So therefore, from this, actually from this and this, I'll write that from these two things, I can write that the number of elements in S is at most k minus 1, and therefore this quantity is at most k. So therefore, it is possible to merge one element from T which is not in S with S such that the union has size at most k, and therefore the exchange property is also holding true. Is that fine? So both S and T have size less than or equal to k, but S has size less than T. So therefore there is at least one element which is in T but not in S, and that element can be taken union with S such that the size of S gets augmented by 1, but then the size of S is still going to remain at most k. Okay. And how about the empty set? The empty set has size 0. So therefore the empty set is also part of this family, because we are insisting that we'll take all sets of size at most k. All right. So therefore this family is in fact a matroid. All right. So now we have seen a matroid. So are there any doubts on this? Okay. So if there are no doubts on this, then the next one is straightforward. Now if you take the family of all subsets of the vertices of size exactly equal to k for a given fixed k greater than 0. They are insisting that I'll take all subsets of size equal to k, then will the hereditary property hold true? That means, can I take any subset of a given set in the matroid, but as soon as so that it still holds the so let us verify the hereditary property. So what does it say? That it says that if A is in I, that means you are taking a set of size k, then will a subset of A, that means let us say proper subset, that means a subset with size strictly less than k, will it be in the family? No, because you are taking only those sets having size exactly equal to k. So anything of size k minus 7 is not there. So any subset of a set here is not there. So therefore, this is not even respecting the hereditary property. So therefore, this cannot be a matroid. Okay. So I think we have a fairly good understanding of what is a matroid and what is not a matroid by now. If you have any questions on these uh, characterizations and which families are matroid and which are not, in fact, all are not matroid except this second last family. You can ask me any doubts. So next week we may meet on Monday, but Mr. Goel has some conflict on Monday, so we may reschedule the class from Monday to Saturday, but it is not finalized. But Saturday is also again. So there is a message on the chat box. Please share previous year's solved assignment question. Uh, you mean in writing? Okay. So I will talk with the NPTEL team, and I don't know how to share the PDF. So you may share your email ID with me. I will try to send you an email. Yeah, so this Saturday is again festivals going on. So Dasara is on uh, Sunday, I think. You can write down your email ID here itself. I will share my email ID as well. So it is not sure whether we'll have the next session on Monday or some other day. But then the important point is after this week also there's going to be an extra session so that you will be notified soon about that session. So I think, yeah, I have shared my email ID with you, Kanimoji. So you can also share your email ID. I will try to send you the previous year solved assignment in PDF. All right, fine. Got your email ID. Thank you. So yeah, so thank you so much for attending. So I'll see you next week. So take care.